We spent 3 or 4 days just factoring quadratics. That's all we've been doing, is working on different methods of factoring and things of that nature. So why do we actually learn how to factor quadratics? Well, it's actually so that we can algebraically solve a quadratic equation. So what does it actually mean to solve a quadratic equation? Well, we're going to just look at a graph of a quadratic here. The graph of a quadratic is a parabola. And when you actually solve a quadratic equation, what you're trying to find is you're algebraically trying to determine the x-intercepts of our graph. Where does that graph cross the x-axis? And some of you will say, well, why don't I just graph it and look at the graph? Well, in this case, you have an x-intercept at -3 and at +2, but the x-intercepts are not always at exact grid points on your graph. Sometimes they're really messy, they're decimals or they're weird fractions and things like that. So to be able to read that off a graph is much more difficult. So we need an algebraic method of finding the x-intercepts of our graph. So what we do is, when we have a factor like x minus 3, we equate it to 0. And we move the 3 to the other side of the equation. So this tells us that x equals 3. That means that this particular graph, if we graphed x minus 3, you would get an x-intercept at 3. If we look at x plus 1, and we move the 1 to the other side, we get -1 as an x-intercept. So these are individual. If we now combine those, if we have a quadratic here, two binomials form a quadratic, and we solve each of these, we equate x minus 3 to 0 and we equate x plus 1 to 0, we find out that we have x-intercepts at 3 and -1. There are two of them. Now if we look at this next statement, our two factors are x and x plus 1. Well, if you equate x to 0, that means one of your x-intercepts is at 0. If you equate x plus 1 to 0 and solve for x, it means your second x-intercept is at -1. So anytime, and this isn't only for quadratics, it's for any equation. Anytime you're asked to solve an equation, what you're being asked to do is you're actually being asked to find the x-intercepts of that particular graph of that equation. Now, basically what the zero product law says is that if we have two values and you multiply them together and you get the answer 0, then one of them has to be 0. So if you have a times b equal to 0, then either a equals 0 or b equals 0. That leads us to solving equations where once we have factors, we equate them to 0 and we solve for x. So we're going to look at a couple of these examples here. We're going to look at example B. We actually have three parts to this example. We have the 8, the x plus 2, and the x minus 7. So we're going to equate each of these parts to 0. Now, 8 equals 0 makes no sense. So that does not give us one of our x-intercepts. X plus 2, if you move the 2 to the right-hand side, you get x equals -2. There's one of our x-intercepts. Here, x is also going to be 7. That's another x-intercept. Anytime you have an x in front of a factored situation, when you equate that x to 0, it's telling you one of your x-intercepts is actually at 0. Then we also have another one at -2 and another one at 7. If we look at these two factors, if I take 2x plus 1 and equate it to 0, and 3x minus 2 and equate it to 0, I first of all have to subtract 1, and then I have to divide by 2. So in this case, I get a fractional x-intercept, which is perfectly fine. That's okay, but that would be something that would be hard to read off a graph on your calculator. Here, we're going to add 2 and divide by 3, and we get a second x-intercept at 2/3. So basically what you're doing when you're solving an equation is you're taking your factors, you're equating the factors to 0, and you're solving for x. And there are your x-intercepts. So if we look at the next situation, They give us a quadratic and they say, okay, we've got x squared minus 9x plus 20. They want us to factor this. Well, we need two numbers that multiply to 20 and add to negative 9. Well, those two numbers are x minus 5 and x minus 4. So now that we have these two factors, we equate x minus 5 to 0, and we equate x minus 4 to 0, and we solve for x. We add 5 to the other side and get one x-intercept at 5. We add 4 to the other side and get another x-intercept at 4. So the solutions of this equation are 5 and 4. Those are the two x-intercepts that we have in this particular situation. So basically all the review we've done in factoring up to this point is going to help us when we go to actually solve a quadratic equation. And that is primarily the reason why we learn to factor, is so that we can solve equations, that we can actually algebraically determine some solutions. We're going to look at a couple of these. We're not going to do all of these. The first one is a difference of squares. So our two factors are x minus 9 and x plus 9. If we equate each of these to 0, we get x equals positive 9, and we get x equals negative 9 as our factors, or sorry, as our x-intercepts. So notice the process is take your quadratic, factor it. Once you have your factors, equate the factors to 0 and solve for x. If we look at part C, the first thing we can do here is we can take out a common factor. Our common factor is 10x, and we're left with x minus 9. So our two factors are 10x equals 0 and x minus 9 equals 0. So if we solve the first one, we get 0 as an x-intercept, because if you take 0 divided by 10, it's still 0. Our second x-intercept is at 9, because if you add 9 to the other side, there's your x-intercept. All right, a couple more examples before we do a bit of a problem. Here, if we look at this situation, we cannot take out a common factor, so we have to use box method. We have to find two numbers that multiply to negative 30 and add to negative 13. Most people would go, oh, 10 and 3. But negative 10 minus 3, yeah, that's negative 13. But negative 10 times negative 3 doesn't give you negative 30. It gives you positive 30. Our values are actually negative 15 and positive 2. So we divide those by our leading coefficient. We simplify where we can. And our factors are x minus 5 and 3x plus 2. So now we have to equate each of these things to 0. X minus 5 equals 0. So we have an x-intercept at 5. 3x plus 2 equals 0. So you subtract 2 and divide by 3, and you get negative 2/3 as an x-intercept. In this next question, you're going to notice that this quadratic is not equal to 0. Before you can solve a quadratic, you must make sure it's equal to 0. So the first thing we're going to do is we're going to add 25 to the left side. And now we have this equal to 0. Second thing, if you notice, we can take out a common factor of 5 from everything. And now we can factor this. Two values that multiply to 5 and add to 6 are positive 5 and positive 1. So if we now solve this, 5 equals 0 doesn't make sense. X plus 5 equals 0 means we have an x-intercept at negative 5. And x plus 1 equals 0 means we have an x-intercept at negative 1. So basically all the factoring you've been reviewing, you're still doing all the same factoring. The one little addition when we solve an equation is we take our factors, we equate them to 0, and we solve for x. Now the difference, you're going to have to read questions really carefully from this point on, because if they ask you to solve it, they're going to want you to find the values of x. If they ask you to factor it, you're going to stop once you have the factors here. Okay, so we're going to look at a couple of problems that we can model using some quadratics. We're going to look at some pictures to help us model these problems, and we're going to set up some equations to help us get a solution. So if we look at this first problem, it says the area of a rectangle is 300 square centimeters. So I draw a rectangle, I label it It's got 300 square centimeter area. It says the length is 5 centimeters more than the width. Well, whenever we solve a question, we have to introduce a variable. So we're talking about length and we're talking about width, neither of which we know, but it says the length is 5 more than the width. So we know absolutely nothing about the width, but we know the length is 5 more than that. So the width is x and the length is x plus 5. It says form a polynomial equation and solve it to determine the perimeter of this sheet. Well, we know the area of a rectangle is length times width. And we know that that area in this question is equal to 300 centimeters squared. So if I expand this, I get x squared plus 5x equals 300. If I move 300 over to the left side, I get this quadratic equation. Now if I factor this, I find two numbers that multiply to negative 300 and add to 5. Those numbers are 20 and negative 15. So if I solve this, I get x plus 20 equals 0, so x equals negative 20, and I get x minus 15 equals 0, so x equals 15. Now, it's impossible to have a negative length or width, so we know this answer doesn't work. So we know x is 15. Well, that means our width is 15 centimeters. Our length is 5 more than the width, so that means our length has to be 20 centimeters in this question. Now, we might think we're done, but if we go back to the problem, it says determine the perimeter of this particular situation. Well, we have 2 lengths plus 2 widths gives us our perimeter. So this is 40 plus 30, which gives us a perimeter of 70 centimeters. Okay, let's look at the next question. Most of you are going to look at this next problem and you haven't even read anything about the problem. And you look at the diagram and you go, what? There's no way I'm going to be able to solve this problem. You haven't even read the question. Don't get freaked out about it. Don't make it look harder than it actually is. So we're going to read the problem, we're going to label some things, we're going to set up some equations, and show you that this is not as hard as you think it is. So it says the diagram shows the cross-section of a water trough who has sloping sides. So this outside, this bold portion is the outsides of the trough. It's formed like a trapezoid. It said the sides AD and BC form 45-degree angles with the horizontal, meaning with that top of the trough. It says the total length of that trough is 36 centimeters. Now, it says show that the area of the cross-section is x times 36 minus x. Well, we've got to look at this as area 1, area 2, and area 3. Because we've got 3 sections we need to find the area of to try and set up this section. They tell us that this distance here is x. And if we look at this, because this is a 45-degree angle, then each of these are 45-degree angles. We actually have isosceles triangles on each side, meaning if this arm is x, so is that arm. If this arm is x, so is that arm. So if we look at this triangle here, how do we find the area of that first triangle? Well, it's base times height divided by 2. Well, the base is x and the height is x, so we have x times x divided by 2, or x squared over 2, is the area of area 1. Area 3 is exactly the same. So if we times this by 2, what we notice is that these 2's cross out, and we actually have an area 1 plus area 3 together gives us an area of x squared. If we look at this middle rectangle, we know the width, but we have to look at the length. This total length is 36, but we're going to have to take off an x on the left side and take off an x on the right side. So this length is 36 minus 2x. You're moving in x on the right and x on the left, so that's what we have here. So for area 2, to get the area of a rectangle, we take the length times the width. So area 2 is going to be 36x minus 2x squared. So how do we get all of these areas? Well, we have to take area 1 and 3, add it to area 2. So we have 36x minus 2x squared added to x squared. Well, if we look at this, negative 2x squared plus x squared is negative x squared. This gives us 36x minus x squared. If we were to factor this, if we were to take out a common factor of x, we get that the expression for the area of this whole thing is x times 36 minus x. Why would you want to generalize a formula for the area of this trough? Well, if I change the dimensions of the trough, if I make this something other than 36, and I add a value or I change x, then I can just use this formula to figure out the area of the new trough that I'm working with. So there you go. A couple of examples of how you can use some solving trig equations to solve a problem. Now it's time to do some work.